So let's start our today's lecture, and it will be based on the acid-base reaction. So we are just taking a very simple reaction using a strong acid, hydrochloric acid, and sodium hydroxide as a strong base. So you react to them, and you get a very simple neutral salt, which is sodium chloride and water. So this is very normal reaction that we study in the uh, the basic uh, chemistry. So yes, this is a very uh, okay. And now we are going to study about this reaction. We are going to take each compound and see how the reactants, why these two stable reactants react to give two different uh, compounds um, when they are already stable, and what makes them to react. So we have to take each reactant first, and then we will also take each product and then see how this reaction occurs and the basic chemistry behind this reaction. So our goal is to see the basic chemistry behind the reaction. So the first question we are going to ask is why the stable reactants. So why the stable HCl and NaOH react. So what makes their reaction possible? So in normally you just study that it's a strong acid and a strong base, and they react to give something which is neutral. So when you hear about the word strong, it means that there is something more energy in this side. So on the reaction side, if you see that you have this reactant and you have a product on this side. So when the reactants have strong, you know, um, kind of something associated with them, and that we say that it is because of the higher energy of the reactants, and they want to get stable. So they want to shift to the side which makes them stable, and therefore they will change into something which is more which has less energy. So there on the reactant side you have high energetic molecules, and they want to go to the low energy. So you have high energy on this side, and you want to shift them to the low energy. And now we will see how this reaction occurs. And normal, we can say yes, this reaction is an exothermic reaction. So when you say it is an exothermic reaction, it's itself as an indication that the reactants are highly reactive, and they want to get stabilized to the lower energy. So that's why the energy is released in this reaction, and so this is an exothermic reaction. So but we want to see that what is the chemistry behind it, how these molecules, these two reactants react when they are already stable, and what makes them behind the basic chemistry behind this reaction, so that next time when you have this kind of reaction, you will be easily able to follow the the reaction. You will be easily able to understand the reaction. So let's start with our first reactant, which is HCl, hydrochloric acid. So HCl is a very strong acid, as we know. Yes, it is. It's very strong acid, and it has tendency to give the you know hydrogen ions very fast whenever it's present in the solvent, for example in water. So it is always present in the H positive and Cl ions. Though this bond is the bond between HCl is is a polar covalent bond, definitely, because the Cl is electronegative, so it is a polar covalent bonding between these two at, uh, atoms. So you have hydrogen and chlorine, and because of this polar covalent bonding between the HCl, because Cl is electronegative and hydrogen is less electronegative, so therefore the shared pair of electron, sorry, you will get here negative here, and you will get positive because the shared pair of electron is attracted towards chlorine because of its high electronegativity. And we must know, it's better to know the value of electronegativity of chlorine, which is equal to 3.16. So it's a good number. It tells you the tendency of chlorine to attract with electrons. And but here the chlorine is not happy because it doesn't want to share this electron with the hydrogen. It wants to take the electron from hydrogen and get transformed into the something like chloride ion. And definitely chlorine has why this is more stable than than the chlorine, because of the, as we know that if you see the stability order, so that is very important to know. And then if you see something that we want to know why it's so, because chlorine has the outer electronic configuration of uh, 3s 3s2 and 3p5, so it needs one electron to complete the octet, and therefore chlorine tries to gain that electron and becomes a very stable electronic noble gas configuration, so it becomes 3p6. So therefore this one is unstable and is reactive. So whenever something is unstable in chemistry, we can say that it's a reactive species. So this is reactive, and this one is quite stable. So this is a kind of less reactive, or almost very non-reactive. Therefore, chlorine in this case, if you see, the chlorine has a tendency to gain that electron from the hydrogen, and yes, it gains, it tries to go into some other position which can give it that completely transfer the electron to the chlorine. Now the next thing that we see here is that our second reactant, which is a strong base, which is sodium hydroxide, which is a very strong base. And definitely there is something we can see here, that when we say strong base, it means it's very reactive as well. But what makes it so reactive, when sodium is already in the position in the plus one oxidation state here, because sodium and hydroxide ion, they are sodium has completely transferred its electron to the oxygen here, and sodium would always love to be in the plus one oxidation state, because we know the outer electronic configuration of sodium is the valence shell. It has one electron in the third shell, so it wants to lose that electron, and it wants to gain a very stable electronic configuration, which is uh, the 2, yes, 2s2 and 2p6. So that is something very stable electronic configuration for sodium. So this is he prefers to have this. So this one is very quite stable, um, and this one is unstable here, because sodium uh, would like to lose it and would prefer to get this noble gas configuration. So yeah, this one is very reactive, so it's very highly reactive with sodium. And this one is almost a non-reactive, or we can say very less reactive ion. But what is the problem with the sodium hydroxide then, when sodium is already in the plus one oxidation state here? So The one more important thing that we need to know is that sodium is always kept immersed in oil, so it is kept in mineral oil. So, and why? Because just to you know um, stop its reaction with the oxygen and water. So it is um, always sodium tries to go get into the plus one oxidation state. So whenever it, for example, reacts with the oxygen, so it forms the sodium oxide very quickly. So it's a very fast reaction, and okay, so yeah, we can do this just to balance the reaction. So it's very quite sodium oxide, because here the plus sodium is in plus one oxidation state, and from 0 to plus 1 it always tends to get this state, as I already explained why. And also with the in case of water, it's very reactive, sodium, with water also. So this one is also exothermic reaction, so it's a kind of dangerous reaction, because sodium would always like to react with oxygen, and sodium also tries to react with the moisture whenever it comes in contact with the moisture. And again, because here the sodium is converted into sodium hydroxide, and you have the another product here released, which is um, hydrogen. So if you see here, um, yeah, and let's balance this. Okay, so this is something that we get when this reacts with the, so you have a hydrogen gas here, and this is also exothermic reaction. So this is kind of the energy is very is released here. So they both reactions, that both means that sodium is here um, change its oxidation state from 0 to plus 1, and so whenever it finds it an occasion to get this oxidation state, it always uses that um, very smartly. Okay, so we, that is why the sodium is always kept immersed in oil in the laboratory or anywhere where it is used. So now the question is that the sodium hydroxide is always the sodium hydroxide, it is in plus one oxidation state already, sodium here. So what is the problem here? And this is minus 1, so sodium has already lost electron, therefore the bond between sodium and hydroxide is an ionic bond. So you have a very strong ionic bond, because ionic bond is stronger than the normal covalent bond. So it's the complete transfer, and due to the electrostatic interaction between the opposite charges, the bond is quite strong. And but there is a problem with the sodium hydroxide, that makes it to react. And what's the problem? The problem is that sodium hydroxide is hygroscopic. So the first is it's highly hygroscopic. So if you see in the lab, you remove sodium hydroxide pellets in openly in the air, and after some time it will be turned into like a liquid. Um, so because it is very much attracted to the moisture, even if it is very less moisture, it gets attracted to that water present in the air. And what makes it highly hygroscopic? Yeah, there are the problems. The sodium and hydroxide ions, when they are in presence of water, uh, they get attracted to the water molecule, because water is a polar molecule, and there are dipole interactions which stabilized these ions. So for example, you have here the water molecule. So yeah, and this is partially positive because of the dipole. Oxygen is a very strong electronegative even stronger than chlorine. So there is kind of something, you know, stability of these ions due to the water molecules. Also with the sodium, if you see sodium, um, there is a stability, and because of this oxygen part of the water, which is partially negative, gets attracted to the positive sodium, and also from the other side. So you have a lot of interactions with the and with the water molecules for both sodium and hydroxide ions. So due to this, sodium always prefers to have this kind of environment, sodium hydroxide, because there the hydration, a very high hydration energy is released. So when a high hydration energy is released, so that means their sodium hydroxide is more is less stable than when it is present in the in the water as ions. So as the hydration energy is released, which stabilize them, so they are stabilized, and therefore they prefer to be in this situation. So yes, this is something uh, that we should know. Oxygen is very highly electronegative, so this high electronegativity of the oxygen, you know, makes it more this prefer to form a strong dipole interaction with the water molecules. So that is very important to know. And this higher electronegativity of oxygen um, makes it a very interactive with with the water molecules, and also with the sodium. There is enough charge present here to attract the water molecules. The second problem with the sodium hydroxide is, the second problem with the sodium hydroxide is this: it's a less robust ionic structure. Ionic structure. So there is the lattice crystal structure, but that is not a very robust one. The problem is that you have a size difference between sodium and hydroxide ions. So we have a large size difference between these two. So they have the size difference, which doesn't allow a compact packing. So there is um, less compact packing. When the packing is less, what happens to the next is that it's less stable. So it has less ionization energy. So you need very less energy to ionize them, to break this bond. So the ionic bond is not as strong as it should be, and that is, I told you what are the problems that makes it very uh, you know very less stable. And now coming to our products that we get in this reaction, and now we see why are the products more stable. Yes, they are. So our product, for example, our first products, let's move to our next section, that's the products. And the first product we have is sodium chloride, and it's a very neutral salt, so it's not acidic, not basic, not strong, it's just neutral. So the pH is around 7 here. And so is it stable than sodium hydroxide? Yes. So in case of stability, if the question will be asked, stability of NaCl is greater than that of sodium hydroxide. So why? It's also an ionic bond. Yes, it is. But the question is why? So Na and Cl, they raise the complete transfer of electron from the sodium to the chlorine. So this is a strong ionic bond. And we need to say why it is stronger than the sodium hydroxide. So the strong ionic bond is because of many factors. The first thing about it is that the size of sodium and chloride ion is almost similar. uh, it's very close. So these ions have very close size. What it helps in, so the packing is compact packing of the crystal lattice. So this the structure tells us that the lattice structure of this sodium chloride is very compact. So there is a strong ionic bond. So the energy need to break this bond is very high. So you cannot, you know, mm, high energetic bond. So there is, you need to have a lot of energy to break this bond. So it's very stable. The structure makes it very stable. And also if the water molecules try to dissolve the sodium chloride, so you have um, yeah, let's keep it on the side. The sodium chloride, and if the water molecules come around it, so they don't have too much energy to break this. Even if, for example, when you dissolve sodium chloride in water, you have the sodium and chloride ions, you know, but if you increase the concentration a little bit, you need to give heat. So this reaction is actually endothermic. So you need to give heat to dissolve these sodium chloride into its constituent ions. And what about the hydration energy when the water molecules, form the dipole interaction with these ions? So definitely there is similar to the sodium hydroxide. So you have the water molecules here. I will just write in this way now. You already understand from my previous lecture. So you have a dipole because it is a kind of partially negative charge here. So it interacts with this sodium and from all the sides. So it's surrounded by the water molecules, this sodium ion, and hence it's stabilized. And yeah, the Cl ion too, of because the hydrogen ions would sorry, the hydrogen part of the water, these hydrogen atoms, because of the partially positive charge, would prefer to interact, would form the dipole interaction with the chloride ion, because being the negatively charged here. So you have a different kind of interaction from different sides. From all the sides, the chlorine is attracted, you know, by the water molecules. Similarly for the sodium hydroxide. So it's very similar to the sodium hydroxide. But here, when you see this part, the chloride ion, the charge, if you see the charge density, the overall hydration energy released is less than sodium hydroxide. So less hydration energy is released. Why? Because the chloride ion, uh, if you see the size of chloride ion, the size of chloride ion is greater than hydroxide ion. So when the size is higher, the charge density of this ion is, what is the charge density? So the charge density is lower, so it has a lower charge density than hydroxide ion. Why? The charge is same, it's -1 here, it's -1, so the charge is same, but the size is, when the size is big, so it means the charge is spread to a large surface area. When the charge is spread to a large surface area, the density becomes less, and when the density becomes less, so this one has, hydroxide ion has high charge density because of the small size. So when the density becomes less, the dipole interaction with the water molecules becomes less, so it has a less weak dipole interaction with water. Let's say weak ionic dipole interaction. So it has a weak ionic dipole interaction with water compared to the hydroxide ion. So we must know, we are comparing it with this ion. So therefore the energy here, the hydration energy released in case of sodium chloride is less than sodium hydroxide. So therefore what we can say, that sodium chloride would prefer to be in this way than this. So this is more stable way when it is sodium and chloride ions, or interact through the ionic bond, than when they are separated. So that's why this sodium hydroxide, sorry, sodium chloride is more stable than sodium hydroxide. Even if this question will be asked to you, you can simply say yes, it's more stable, sodium hydroxide than sodium chloride than sodium hydroxide. So the reaction prefers in the forward reaction, and it's an exothermic reaction. Now coming to our last part of this reaction is the second product that we have in this reaction. We know what was our second product. Yes, it was water. So let's see, water. How is this water? Is it stable? Water is stable. Yes, it's very stable. Yes, stable. Why? Because it has a bent structure. We know that water has a bent structure, so you have, so yes, it has a bent structure. So let's make it a little, okay. Yes, why it has a bent structure, that we already know, because it has two lone pairs oxygen, and these lone pairs, they have the repulsion between, because lone pair repulsion is greater here, so there is a repulsion between these two, okay. And then it pushes, there's a repulsion between these two as well, bond pair and lone pair on both sides of oxygen, and then that's why this becomes a bent structure here. But we are not concerned with how the bent structure is here right now. We are concerned with what is the importance of the bent structure in water for its stability. So we know the dipole from the positive to the negative end. The direction of the dipole is this, and the lone pair have their own dipole. So you have a kind of four dipoles in the water molecules, and finally all the dipoles are directed in one particular direction, and the dipole reinforces, which increases the overall dipole moment for a water molecule. So the overall dipole moment of water molecule is very high, so it's almost equal to 1.85 dBi. So the dipole moment of water, somebody will ask you, so this number is a very high value, and don't say it is just 1.85. 1.85 is a very good value. It's a very strong dipole, and if you see the single OH, it is 1.5, but overall, if you see the single OH bond, the dipole of this bond is equal to 1.5 dBi. Okay, but the overall for the water molecule, the dipole is this one. So don't get confused with the arrow here. If I see it like this, so overall dipole is on this side, okay, in the upward direction. And what is importance? The dipole moment, it means that it has a strong polarity. So that means the polarity between oxygen and hydrogen increases when the dipole increase. So you have a very strong dipole bond on the both sides of oxygen, and that means it's when the bond dipole is strong, the polarity is increases, and when the polarity increases, the stability of the bond increases. Therefore, it's quite the polar strong polar covalent bond. Let's write it in like this: strong polar covalent bond. And strong polar covalent bond means highly stable. So water is quite stable, okay. And then HCl, if you see HCl here, there is only a single dipole, because there is a polar covalent bond, but this is just a single dipole, and the dipole moment of this is equal to 1.08 dBi of so the hydrochloric acid has a very, the HCl has a very low dipole compared to the water, and therefore the strength of the water is very, the water molecule is more stronger than HCl. So if the question is asked to you which is stronger, so the which is more stable, so you have to say water is more stable than HCl. So in general, finally we can say, to sum in summary, we can say yes, the high energetic reactants, because sodium hydroxide and hydrogen chloride or hydrochloric acid are very strong, have a very high energy, and they try to go to this side, which makes them less energetic. That's why this reaction is quite favorable. And this, I would like to write it again the, from the beginning. So this was our reaction, the original reaction that we discussed today. And what we discussed today, in summary, I would like to say you that you have a strong acid and a strong base, and we could form very stable. So they are very stable products. So they are stable but less stable. So because of this less stability, the reaction is um, tries to go to the stable direction. Okay, so that is I hope that you understand this reaction, and next time when you have this kind of reaction like strong acid and strong base, you will just be able to know the chemistry behind the reaction. So that's more important, to know the chemistry behind the reaction than to just remember just a reaction. So we have you know tried to find out all the basic chemistry behind this reaction. I hope you like this lecture. We will have the next lecture soon. Thank you.